All right. Well, thanks for joining in to this tech talk. And the topic today is remote sensing, classifications, and uncertainty. If you have watched or attended our previous tech talk, recall from that tech talk that whenever we have a sufficient number of good training sites, we can expect good image analysis or good classification results. Now, that sufficient number, you might recall, that sufficient number depends upon the inherent variability of the thing we're trying to map. Now, we could interchange that word map with classify, the thing we're trying to classify, or the thing that we're trying to extract from the imagery. It also depends upon the size of the project area. If we are doing a classification over a project area or a study area about the size of Bannock County, Idaho, then that number of sufficient number of samples is going to be quite a bit smaller than if we are doing that same classification across all of Idaho or across all of the United States. And that sufficient number also depends on the number of other competing things found in the same area. Recall that we have targets and we have non-target features of interest. So let's walk through the process. Let's say I want to create a map showing where surface water exists. Surface water then is our target, and anything that's not water is our non-target feature. So I created a sample site point feature class using ArcGIS Pro. What I did is I on-screen or manually digitized visible target and non-target features. And I used the 2019 NAEP, that's the National Agricultural Imagery Program, Imagery, that was collected on August 11th, 2019. This particular imagery was collected on August 11th. And this is pretty nice imagery, of course. It is sub-meter in size. It's actually 0.6 meters by 0.6 meters, a nice square sitting out there. And also, by the way, FYI for you, the 2021 NAEP imagery, as far as I know, I believe has been collected or almost been fully collected. And so we'll have a new set of even more current aerial imagery to work with in the not too distant future. Well, here's our study area. You might recognize this. It is part of Idaho right over here. This little rectangle is this same larger rectangle right here. And the blue points that you're looking at represent target sample sites, in other words, water. And the red points represent non-target sample sites, in other words, the not water, non-target sites. The next step is where we need to acquire satellite imagery, because what I want to do, of course, is I want to classify that entire study area as water and not water. And I don't want to have to, draw polygons all over the place, or certainly I don't want to click more or less every pixel and examine it manually and determine, is this water or is it not water? Those sorts of things. So I'm going to rely on Landsat satellite imagery to help me out. Now, recall also from our previous tech talk that what we want to do is we want to acquire satellite imagery, classifiable imagery, in close temporal proximity to the sample site collection time. Recall that aerial imagery that I used for my manual heads-up digitizing was acquired on August 11th. So we want to get some satellite imagery that was acquired at around that same time. And using the USGS Earth Explorer, I was able to locate and download Landsat 8 OLI imagery that was acquired just a few days before that aerial imagery was acquired. It was acquired on August 4th, 2019. Okay, so one of the things that we're certainly going to want to do, and I should mention this as well, is once we have downloaded that satellite imagery, of course, we'll have to extract it, and that's absolutely free. All you need is a user account, and that's also free from through USGS. Locate that imagery, and then the imagery of interest, download it, and away you go. So then you extract it on your machine. And the imagery that I downloaded was what's called level 1 imagery, all the different bands that are available in Landsat 8. And then to kind of prep that data, what I did is I atmospherically corrected that data using Imagery TerraSet software. And we're going to look at Imagery TerraSet here more closely in just a little while. Now, I also need to prepare my sample sites. So to allow for an independent error assessment. Now, this is important. We don't want to classify the imagery with all of our sample sites and then validate the same imagery or the resulting imagery using the same sample sites. That wouldn't work. That's called a dependent error assessment, and it's going to make it look really, really good. Okay, but it's not really reliable to do that, simply because what happens if we move that pixel just a little bit to the left or to the right, a little bit to the east or to the west? Well, we might not really have such a good classification after all. So we're going to take all of those sample sites that I previously prepared, the red and blue dots, and I'm going to split those things into training sites versus validation sites. Now, when you have a small number of sample sites, and we kind of do for this study area, I will make a split of 50-50 or sometimes 70-30. 70% of the points being used for classification training and 30% used for validation. And we want to have at least, ideally, about 30 points for validation per class. In our case, we only have 2 classes at this point, water versus not water. So we want to be aware of that as well. Then what I did is I rasterized those points in ArcGIS Pro. And that's a simple process. We take the point feature class and convert those to rasters. And I always like to use TIFF or GeoTIFF file format. That works very, very well in both ArcGIS Pro and Imagery TerraSet. Now, here's our remote sensing software. This is a screenshot of Imagery TerraSet. Yes, every piece of software has a little bit different interface, but really not too different, right? We have a very large map area over here. And what I'm looking at is an atmospherically corrected band, one of the bands from Landsat 8. And this is from this exact study that we're talking about right now. This happens to be band 1, which is coastal blue, the coastal blue band. That's what it's called. So again, I imported and atmospherically corrected the LT Landsat imagery. And then I also imported the training and validation TIFF layers. Then what I did is I took that input Landsat layer and all the other data, and I clipped what Imagery calls window. I windowed all of those layers to accelerate all the processing. All the processing will then go faster. We're dealing with fewer pixels, fewer rows and columns in those rasters, and of course, it's going to write smaller files on the hard drive as well. So it usually pays off to do that, and it's pretty important. That's just a little window tool, very, very easy to run this sort of thing. And then I'm going to start classifying water versus not water. So I've already separated water from not water. Well, that sounds pretty simple. I could zoom in and look around at those 30, 40 points, and that was pretty easy for me to do. But of course, we have probably hundreds of thousands of pixels in the study area, and I don't want to do that by hand. So what we're going to do is we're going to start by exploring what's called spectral signatures of these target and non-target features. So in Idrisi Tierset, the tool is called make sig. So we make a spectral signature file. And then we're going to use the sig comp modules. Think of those as geoprocessing tools, the word modules. So make sig, pretty easy process. Again, we fill out this dialog, we click OK, and then we run the sig comp signature comparison chart is what it's going to create for us. And this is what we get. Okay. So what's happening here is in red, we see the spectral signature for water in the band 1, coastal blue, band 2, blue, band 3 is green, red, near infrared, shortwave infrared 1, and shortwave infrared 2. Those are the basic visible and not so visible to us bands that come with Landsat 8. So I've got 8 bands of Landsat imagery. And what we like to see is good separability between our target and non-target features. And what we don't see that. We don't see good separability here, or here, or here, or here. In fact, we have quite a bit of overlap. So if this was all that we had to work with, just the visible bands, we would actually have trouble having a good, reliable classification at the end of it. But once we get into the, or we get outside the visible bands, near infrared and shortwave infrared, we have very, very nice separability between water and not water sample sites. So that looks promising when we see something like this. So this is good separability, at least in those couple of bands, those 3 bands. And in this case, since it's such a simple classification, water versus not water, we can use a simple classifier like maximum likelihood. The module is called max like. And we fill out this dialog box. The signatures are water and not water. And we give the output image the name of water, not water. So that's how imaginative I am. Then, of course, we click OK. That's the result. Hey, it actually did a pretty darn nice job. It looks like it completely mapped the American Falls Reservoir. There's obviously some wider parts of the Snake River that it's detecting here. And I wouldn't doubt that if we zoomed up on this, we'd start seeing some little speckled red dots as well here, the water. And it just happened to color those pixels red. It would have been nice if it had chosen blue, but it just doesn't do that. So that looks like it worked out pretty well, but that's just a visual review of the output classification. How did we do really? Yeah, sure, it looks pretty good, but let's look at this statistically. So we're going to test the classification performance using an error matrix that also includes the kappa index of agreement test. And notice that when I'm filling out the error mat tool, that I am using the validation sites layer here. I trained and I classified, or I classified with the training sites layer, but now I'm validating with the validation sites layer. And there, once again, is our water, not water output image. So I click OK. How did we do? Hey, whoops, pretty darn well. This is our uncertainty. I had 23. Remember, I like to have 30. We didn't quite make it. Could have laid down some more points. Might have been, well, it couldn't have improved it any more because it did a perfect job. And what we like to look at is this kind of stair-step appearance, 1 versus 1. So how often when we had a training site that we know, or a sample site that we know was class 1, water, how often did it actually classify that as water in the output image? 23 out of 23, perfect. Well, we knew that 78 of our points were not water. How often did it get that right? It did a perfect job as well, 78 out of 78. And then we look at this here, 101 points in total and never got them wrong. So boy, it did a wonderful job. The error is absolutely 0. Now, this is an absolutely simple classification, and in reality, in practice, we normally don't get 100% accuracy or a rate of 0 for error. The other thing we want to look at is with disproportionate sample sizes, which we do have, right? We like to see 30 and 30 or 78 and 78 or something like that. We also, in this case especially, we want to look at kappa, because kappa does an adjustment for disproportionate sample sizes. And again, it did such a wonderful job that we got a score of 1.0, right? That's as good as you can get. In other words, that's telling us that our classification performed 100% better than a chance random classification would ever do. So that looks real good. That's the real basics of it. But let's try something a little bit more challenging. Let's say we want to classify water, cultivated agriculture, and rangelands, or native grasses, those sort of things, native sagebrush steppe. So what I did is I went back into ArcGIS Pro and I modified my not water sample sites and split them up into cultivated agriculture and rangelands. Then I repeated the process to create spectral signatures. And this is our signature comparison chart. And once again, we're seeing very poor separability in bands 1, 2, 3, and 4, the visible bands. We're also seeing poor separability in the shortwave infrared bands when we're comparing cultivated ag and rangelands. We have overlap, so we can't expect a good classification. And in fact, when we only have one band that provides separability, that's like putting all the eggs into one basket, and it's not good. So we really shouldn't expect very good classification results when we're relying on just this separability. And this is the separability for the training sites, not necessarily the validation sites. But what if we add more bands? You see, using that input data from Landsat, we can create what's called band ratios and extract principal components from principal component bands from that source imagery. And we do that using PCA, principal components analysis. And this can enhance separability. So now what we have here is we have good separability with band 2, that happens to be a normalized difference vegetation index. That's a simple band ratio. We have good separability with band 3. Notice that they don't overlap anywhere. That's our MSavvy2 modified soil adjusted vegetation index version 2. We have good separability with PCA composite 3. That's what appears as band 6. Actually, excellent separability here with that principal component analysis, and still our near infrared band now shifted over to band 10. But look at how much better separability we have with these band ratios relative to the raw bands. Even the one that had good separability before really doesn't separate them as well as some of these other ones do, PCA and the band ratios. Okay, so now whenever we have more challenging classifications, better classifiers are needed. So instead of using something like minimum distance to means, maximum likelihood, let's start considering using artificial neural networks or artificial intelligence-based classifiers. They sound kind of scary. They sound like they're way the heck out there. I can't do that. Well, sure we can. In fact, they're already available to us in software like Imagery and ArcGIS Pro. We have the classification tree analysis, CTA. We have random forest, support vector machine, and machine learning / deep learning. Now, by the way, classification tree analysis, that's what I'm going to be using here in just a little bit. But random forest is essentially a little bit of a play on words here. Random forest is an iterative we're going to run it lots of times, or the machine's going to run it automatically for us lots of times. It's going to run classification tree for us lots of times. So that's the, I guess, play on words. We have one tree, but if we run it lots of times, now we have a forest. Okay, so that's what that's all about. So here's an advanced classifier. And another advantage of an advanced classifier is not only does it do a better job at figuring out the difference between water, rangelands, ag, and you name it, lots of different classes could be out there. It also allows us to add other layers like elevation, slope, aspect, other types of raster data that can also help us differentiate one feature from another or one class from another. And that was always kind of frowned upon with those traditional classifiers because they had such a huge difference in their numerical range, right? Their pixel depths and all that stuff. But with these advanced, essentially neural network, advanced artificial intelligence type of classifiers, it's absolutely perfectly fine to do that, okay? So what do I have here? Well, I ran the classifier, and of course I called this one CTA 3 class, and it broke things down, but let's see how it did this time. Once again, good results are possible. And what do I mean by a good result? Well, we normally consider greater than or equal to 70% accuracy per class and overall as a good classification. And once again, I'll remind you, we rarely see 100% accuracy across the board in practice, but we did in this case. And it's still a simple classifier. We only had 3 different classes and a relatively small study area or project area, but it did a great job. Probably wouldn't have done so well if we didn't create those NDVI and the PCA, and probably wouldn't have done so well if we didn't use CTA. But it did a really nice job for us once again. Look at the stair-step pattern, analyze all that stuff, look at your class by class error assessment, and to categorize or determine the accuracy, you just take this number, the error rate, and you subtract it from 1, and that difference is, of course, your accuracy rate. So we had a 1.0 or 100% accuracy in this. Nice job. All right, so that brings us to the end of our tech talk for this session. I'll open the floor. Feel free to unmute yourself or pop your question into the chat line. I'd be happy to answer that. Any questions for you?